So about the 4 paradigms of research. So let's see where does atomistic simulation fits into all of this. So traditionally, since the beginning of, let's say, science and research and trying to find anything out by humans, we started with empirical science, just observing nature and seeing what happens. Then during the Renaissance and a little bit later, people started formulating theories. They made more rigid observation of nature and tried to formulate laws that govern the movement of things and so on. Newton is a great example who formulated classical mechanics. Then a little bit later in the 20th century, when computing power was getting more and more accessible, it started to become more and more feasible to do calculations, simulations using the computer. And in the most recent times, the amount of data that is being generated by simulation, by all the different calculations that we do with countless methods, is generating so much data that we are training algorithms to learn from this data and provide new insight without actually doing the calculations. So we are right now at the shift between the third and the fourth paradigm of research. And actually, the artificial intelligence that we are creating is not that far behind us. Recently, a colleague of mine shared a paper with me that's already 10 years old, that an artificial intelligence watching a video could derive the laws of classical mechanics. Without any input from humans, they derive Lagrangians, Hamiltonians, and so on that are used to describe classical mechanics. So maybe it's a bit scary, but we have to remain one step ahead before the machines, so we don't become completely useless. So traditionally, the computational science has been lumped together with theoretical science. Actually, when I did my PhD in computational, we didn't have a computational department at the university, and most physics departments don't have computational departments. They are just together with the theory people. And it's not always great, because sometimes the actual experiment very much resembles the computer experiment, let's say. So this is an example of a molecular dynamics simulation. So we calculate the forces that are acting on atoms or on different species, and we propagate this dynamics in time with some time step. And this is similar to the experiment that usually goes like this: that in the first step we prepare somehow the sample. It's a very simplified picture. Then we connect some sort of experimental apparatus to the sample, and then we gather data. And the longer we gather the data, the more we average, and the more reliable our measurement appears. The longer the measurement, the lower the error. And the computer experiment, in this case the molecular dynamics simulation, very much resembles this. The first step is to prepare the model system. You set some initial positions, velocities of the particles, of the atoms. Then you do some steps of the molecular dynamics for the system to thermalize, to reach thermal equilibrium, for instance, to forget we say it like this, to forget the initial conditions that were imposed on the system, until some quantity that you want to calculate stops fluctuating. Well, it doesn't stop fluctuating, but it stabilizes. And when it stabilizes, you start gathering the data, and this is your production run, which directly corresponds to gathering the data. The longer you run the simulation, the more accurate your outputs will be. Here's the outline of today's talk. I've already covered the 4 paradigms of research and what I call the computer experiments. Now I'm going to move into a short and the least amount of equations that I can put introduction to methods, the density functional theory. Then I'm going to talk about material properties that can be derived from different levels of modeling, so density functional theory and beyond. Then I'm going to tell a few words about how data is managed in computational material science, which is getting more and more important, the data management part. Then I'm going to show a few examples how high throughput screening can be used to select some candidate materials with some desired properties for specific applications. Then I'm going to say what are the descriptors of data that can be used to describe both experimental and computational data. And here it's important the need for clean experiments that provide clean data that can be very well described. And at the end, I'm going to finally reach how machine learning can be used to learn something from the data. First is the short methods introduction to density functional theory, which has been really the workhorse. And I specifically highlighted this work because it's been probably the most important method in the materials calculations that has been devised ever. Here are the number of citations of articles referencing density functional theory in the text, and the number of patents on the other axis. Unfortunately, the data only goes to 2015. It would probably be even higher today. So this is the number of papers per year, not a cumulative number, but how many were published in a certain year. And this guy has been instrumental to the success of these methods. This is Walter Kohn, some rollerblading grandpa in California. That I'm going to now highlight what was his contribution and how it all fits in in what we want to do with materials science, the computational methods. So, what is the central problem at the heart of everything? Is solving the Schrödinger equation. You probably know it from the course of quantum mechanics. On one side, you have the Hamiltonian acting on a electron wave function, and on the other side, you get the energy. If you know, if you can solve for the wave function, you can determine energy, you can determine actually everything about the system. But to do this, you have to find the wave function that depends on all the electrons that are inside the system. If you have a hydrogen atom, it's easy. Yes, there are not very many electrons. You can write the solution on a piece of paper. But when you have a system that consists of many atoms, sometimes the number of electrons can reach like 1 mole of electrons, so 10 to the 23rd power. So it's completely impossible to solve it directly, which was found out very early in the founding days of quantum mechanics. Dirac already said that the difficulty lies in the exact solving of this equation. So there was a need for approximate practical methods, and he already knew that in 1929. Only a few years after actually Schrödinger formulated quantum mechanics in such a way. Then some clever ways were devised to actually find out the electronic ground state of the system, and it relies on 2 theorems: the Hohenberg-Kohn theorem and the Kohn-Sham equation. So you can see Kohn's name in both of these, and this is why he was very important to finding this. So the Hohenberg-Kohn theorem states that every quantity about the system can be expressed. We can reduce the problem to find not the whole wave function, but just the electronic density. And another clever way is to find the ground state of a non-interacting system. So the wave function of the interacting electrons, each one electron interacts with the other 10 to the 23rd power electrons. It's completely impossible to solve. But Kohn and Sham have proved that you can instead solve a simpler, much simpler problem of non-interacting particles that give the same electronic density. So how it looks in practice? We have 2 systems here, the interacting system and the non-interacting system. And if we know the external potential, we can find out the full wave function depending on each electron and each of the positions. this is here, this is the wave function, this is the ground state wave function, and we can find the ground state density. And then we are done. We cannot go any further. The same for non-interacting system. We know the constant potential, we find this is an important, not the full wave function, but single electron wave function is very much simpler to solve, and arrive at the same density, but also nowhere else to go from here. So the theorem introduces those two arrows. From the density, you can derive the potential. And actually, that you can iterate. You can start with some guess of the density. For example, into the local density approximation, which was the most popular in the early days of DFT. And you calculate the potential. With the new potential, calculate the wave function and find the new density. Then you compare the old density and the new density. And if you have convergence, you are done. You have found the ground state density. But still, you cannot. You can calculate this system, and you can calculate the system, but there is no connection between them. And what Connett-Sham did is actually provide the connection. So if you solve this system on the right, which is much simpler, you get the density, and you can actually find the solution of the actual interacting system. So it was brilliant, and it's really put forward and started a completely new field of computation. So this is what it looks like in a sort of cartoon picture. So when you solve the Schrödinger equation, you get some ground state, the minimum energy, that depends on the wave function of 10 to the 23 variables. And when you do DFT, you get a slightly different. It's a slight approximation, but you get also the ground state that only depends on 3 variables: x, y, and z. Much simpler, right? Well, it's I also make some terrible simplifications here, but I don't want to get into detail. If you want to explore this field, I invite you to do so. It's very exciting right now. So the rollerblade. Let's get back to the rollerblading grandpa. So he actually received a Nobel Prize for his equations and theorems in 1998, the same year as the rollerblading picture. He received the Nobel Prize from the Swedish Academy, and really things moved forward from there. And this is his legacy. Unfortunately, we won't find out what more could he devise, because in 2016 Walter Gone has passed away. But his legacy lives on, and we all use it to derive fantastic things about the materials that we use every day. Okay, so what kind of properties can we actually derive from density functional theory, from similar modeling? There are a few levels. First level is something that you actually have to impose. You have to set some atomic positions, nuclear charges. This is just your input, or sort of your gene. This is a term used in the machine learning community. Then, if you do a density functional theory calculation, you can directly derive the total energy, the electron density, and so on, elastic constants, the geometry of the system, the crystal structure, the lattice constants, and other things. So this is the level 2. At level 3, so you have to do a more sophisticated calculation, use combined DFT with different methods, and then you can derive excitation energies. You can derive band gaps, electrical conductivity, phonon spectra, so how atoms move in a crystal, thermal conductivity, and so on. And the fourth and last level of complexity, you can derive properties that combine very different qualities of the material. So you can directly calculate thermal conductivity and electrical conductivity, but you cannot do it in a single calculation. You have to do two calculations and then combine them, and this is level 4. For example, to derive something like a thermoelectric figure of merit, I think it's good for you to remember this particular property. You have to derive it from level 2 and 3. And as you can see in the last column, we can see how much data does it take. So level 3 is the one that takes the most data, and level 2 it's gigabyte. It goes into gigabytes and terabytes of data for a single calculation. So it's really important to know what to do with this data. But I'll get in there in a minute. But a few more words about the thermoelectric figure of merit. So it depends on, as I said, on the electrical conductivity and the thermal conductivity by the way of three properties: the Seebeck coefficients, the electrical conductivity, and the thermal conductivity, all multiplied by temperature. And this is an example of a descriptor. So a descriptor is a computationally addressable matrix that quantifies the full potential of a material to fulfill a specific purpose. So that means if you are looking for a good thermoelectric material, you just look for a material that maximizes the thermoelectric figure of merit. And it's important for machine learning to find such quantities that can be used as they can be assigned to our data as sort of metadata. So you can search for them and compare the properties between different materials. So now, how to manage all of this data? You have to do it. You have to do it by checking one of the material repositories databases. They are getting more and more robust. More and more information about materials can be found in, for example, NOMAD, AFlow, OQMD, or Materials Project. They are all repositories that fulfill a specific, let's say, approach in data collection, which is called the FAIR principle. You might have heard about it, but if not, I think it's also a good idea to learn this acronym. So you have to make sure that the data is findable, accessible, interoperable, and reusable. What does it mean? Here's an example from the Materials Project repository. The data is findable and accessible by a human. You can just put the name of the compound that you are looking for, but you can also click on different atoms. And for example, if you click Zn and O, you can look for all the materials that have this chemical formula. So zinc oxide. You can find the most stable ones, but also the more exotic phases that exist only, for example, in very high pressures or very low temperatures. And also, your data needs to be interoperable and reusable. So when Kohn was working on density functional theory, there was one theory, but then everyone wrote their own code to calculate the material properties. So these are a few codes that are indexed by the NOMAD repository, and they actually have data from 40 different programs. So you have to make sure that all these programs in the end produce the data that is that can be comparable. The formats have to be unified. They have to use the same units. They have to have a unique description of the data. So actually, you cannot work with all the developers and have them agree on a standard. These cartoons, when we have 13 competing standards, so then that's unified, and the next stage is we have 14 competing standards. So the repositories do it themselves. They have their own in-house formats. They parse the data. They assign even DOI, so you can cite the data like you would a publication. Okay, so if we have this data, then what can we actually do with it? So I'm going to talk about high throughput screening, which means that we put a lot of candidate materials through a sort of funnel, some sort of sieve, that at the end we do calculations on the computer and we receive less materials. This is the cartoon on the right. Yes, from many materials we have only 3 candidates that, for example, we can then check in experiment. And in actual experiment, this would so the cartoon on the left, this would go another way. We would just take material one by one. We would measure some sort of quantity, and then we would receive actually more candidate materials because we only measure one thing. And here we have all these steps that correspond to different electronic structure calculations. So in this example, you can find it has been applied to transparent conductors. So you can have N-type transparent conductors, you can have P-type transparent conductors. The most prominent example is ITO, or indium tin oxide, which is the N-type layer that is used in electronics as the conductive layer. So a sort of mission that a large part of the community is to find the P-type transparent conductive oxide, which would hugely extend the range of applications. So a few criteria are applied to the materials. It has to be stable, it has to be transparent, conductive, and it has to be dopable. What does it all mean? For stability, it means that the formation energy has to be negative. So if you have zinc oxide, I will use this example, if you calculate zinc and oxygen separately, then when you combine it, it has to have lower energy. So it has to be thermodynamically favored to form. Then it has to be transparent, which means the band gap has to be above a certain level. This is sort of a vague description, what you actually call transparent, but in this particular study, the authors decided that it's band gap above 2 electron volts for it to be transparent. Actually, zinc oxide or the indium tin oxide that I mentioned earlier has a band gap above 3.4, so it's mostly transparent to visible light. It only absorbs some ultraviolet light. Then it has to be conductive. So the descriptor is that it has to have a low electron in case of N-type and low Hall effective mass in case of P-type semiconductors. And it has to be dopable, which is the most vague, I guess, and the most computationally expensive property. The branch point energy has to favor N-type or P-type by lying either in the conduction band or the valence band. It's not very easy to explain in a short presentation, but anyway, these calculations are ordered by computational complexity. So it's most easy to calculate stability, and you already filter out 50% of all the materials. So you only have 50% coming to the transparency calculation. Then it's a little bit more hard to do it, but you also filter out, and it's a little bit higher to do the conductivity and so on. And you end up with the final set of materials. So the quantities that I described are descriptors of data. So then you can set, for example, the branch point energy as an important descriptor that you have to include in your materials database. But descriptors can be also quite a bit more complicated. Here's an example from a whole other field of study, from chemical engineering, from catalysis. So this is actually an example of an experimental study that produces very clean data that might have as well been simulation. Very nice experiment where you prepare the catalyst, you do some characterization, the fresh catalyst, then you activate the catalyst, measure its reactivity. So this is what's most important for the catalyst to be active, to be able to carry out some sort of chemical reaction, and you still do more characterization. So very sophisticated and a huge number of measurements that can be used to derive some sort of property. So then you have to think very hard how to combine all these properties into a single descriptor. And this is what the authors came up with from Annette Trynschke from Fritz Haber Institute in Berlin. So they derived a descriptor that features many qualities that reflect how the catalyst triggers the process, how it enhances the reaction rate, and how, for example, it boosts or hinders selectivity. So we want the catalyst to be efficient but selective. We don't want any parasitic reactions. So this is a very complicated descriptor that we end up with. And if we use this data, if we do clean experiments, we can index it the same way that we do the computational data. It's very very useful to all the community, not just the experimentalists, but also the computational people. So now let's see what can we do with machine learning from data. So here's a very simplified cartoon. We have some descriptor, we have another material property, and we get results like this. If we fit one model, a single linear model to the data, we don't get very good results. But if we think a little bit harder, or we let the machine think a little bit harder, it can find that actually there are better fits. If you split into two, you can fit the data here to the red points and another property to the blue points. And this is, as I said, very much simplified, but has also been used by the Fritz-Haber Institute, but by the theory group Sergei Levchenko, to calculate catalysts for CO2 absorption. So they did calculations and they came up with two possible subgroups. So there are catalysts that lead to a small angle of the absorbed molecule, because normally CO2 is linear. And when you absorb it to some sort of surface, you have to change its electronic state, and then when it does change the electronic state, the geometry changes to lower angle than 180 degrees. And another thing that changes other than the angle is the bond length between carbon and oxygen. So they have come up with two subgroups. One that leads to small angle and the other that leads to large bond length. And they plotted it here compared to the gas molecule with some sort of dipole moment. So if you change the angle, then you break the symmetry and the CO2 molecule receives a dipole moment. So you can compare actually which material can lead us close to this line. So there are some materials that fit both subgroups actually. So they found out that the small angle is more important because more blue points lie close to the red curve. But without dividing into subgroups, if these were all lumped together in one category, it would be very hard to see what are the possible candidates. We have to try all the black points that are close to the line, all the way through the graph. But this way you are narrowing down by some quantities that here they call them selectors, but it's interchangeable, selectors and descriptors. So they set a large number of descriptors for the small OCO angle groups on the left side, and on the right side they selected some quantities that qualified the material to be in the large bond length group. So there's of course also the possible contribution of clean surface science. If you do an experiment in ultra high vacuum, very selective, introduce a specific number of molecules even to the surface, you can calculate. You can actually measure some of these quantities. Well, some of them are very hard to measure and very easy to calculate because, well, you can do anything on the computer. You can just set any system you would like. So this is what they got from applying the machine learning scheme, which saved internal very much computational time. Okay. So, again, about the paradigms of science, as I demonstrated, we are right about here, or probably even further. This was in the year 2010 that we are here. So we are moving forward into the big data-driven science. We get more and more information from analyzing the huge number of calculations, and this is the way it's progressing right now in the community. And if this interests you at all, I would recommend you highly to check a conference that is happening last year. It's called the Sci-K conference, and it normally happens every 5 years. So there was a conference in Berlin in 2010. There was a conference in San Sebastian in 2015, which was my initial contact with this field, and I got hooked. It was amazing. So I recommend you to check out the 2020 edition, which was actually postponed to 2022. They really didn't want to do an online event. This is a huge event in the community. You can expect like 1,000, 2,000 people talking in 38 symposia, 6 parallel sessions happening all the time. So it can be a little bit overwhelming, but it's good to see a big picture and find something for yourself. If you are a fresh student or thinking about doing PhD studies, I highly recommend this field, because there are some quite big changes happening right now. Okay, so thank you. Here are some contact data to me if you want to get in touch and talk about this more.